Hello, class. So we're still in chapter 4, right? We're almost done. I believe this is last thing. This is last example, just generalizing variation of parameters. Okay? So 2 videos ago, we worked with this ODE. Right? We found the complementary solution very easily. And then we used variation of parameters. Using the formula from that I gave you before, right? For variation of parameters, how they generalize. Oh, and remember that I fixed, right? So I had W sub k on the denominator, right? So it's correct here. I wrote it wrong here, but I fixed that. Okay. So we had these determinants that we had to find. And since they're 3 by 3, we don't know how to do it by hand. So what did we do? We did it in Mathematica. Right? So we did that in the previous video. I'm just going to write the results here. So W1 we found was, sorry, just the Wronskian, sorry, just W, not W1. So let's do a different color. W ended up being cosine squared plus sine squared, which is 1. Right. W1 ended up being cosine x times sine x plus sine squared x tangent x. Okay. W2 ended up being 0. W3 ended up being 0. Right. So now we can write equations for each of the u sub I primes. Okay. So u1 prime is going to be W1 over W, so cosine x sine x plus sine squared x tangent x, all over W, which is 1. Right, so it's just itself. It's just W1. Now, U2 prime is W2 over W. W is 1. W2 is 0. So this is just 0. U3 prime, it is W3 over W. W3 is 0. Right, W is 1. So you get 0 over 1, which is 0. So really, there's only one complex integration here. Right? Because when you integrate U2 prime, so let's solve U2 prime and U3 prime because they're really easy to do here. So let's see, integrate U2 prime. Right? If you integrate both sides, what do you get? Right? So here you get U2. On the other side, you get a constant, right? A specific constant, right? Oh, sorry, an arbitrary constant of integration. Now, remember that this constant can be anything for us. In particular, we're going to just set it equal to 0. Sorry, C equal to 0. So set C equal to 0, which implies U2 is going to be 0. Now U3, the same thing is going to be 0. So implies U prime of 3 equals 0, right? The same thing, integrate both sides. The arbitrary constant can be anything we want, right? So we set it equal to 0. So all we need to do is integrate U1 prime. Right? So U1 prime is the integral of sine x cosine x plus sine squared x tangent x dx. Now, both of these are easy to do if you separate it. This one you can do with a u substitution. For example, let u be equal to sine. The u is cosine dx. So this one's easy by a u substitution. Here, you also can do a u substitution because you can write this as sine cube of x over cosine. Just rewrite tangent as sine over cosine becomes this. Let u be equal to cosine. Du equals sine at negative. Du equals negative sine x dx, or negative du equals sine x dx, and they are easy. Right? So let's do that real quick. Here we let u equal sine x du equals cosine x dx. Right, so we get the integral of u du. We get u squared over 2 plus a constant, which again, we're not interested because we're only interested in one specific solution, u. Right, so we set it equal to 0 for the constant. So here we get, so u is sine x, we get sine squared x over 2 is equal to u1. Right? From this work here. Now here we do the u substitution, u equals cosine x, du equals negative cosine x dx, sorry, negative sine x, right? Or multiply both sides by negative 1, negative du equals sine x dx. Now, wait, does this substitution actually work? I think, yeah, no. Yeah, this is fine. Yeah, the only problem is going to be that we have a sine cubed on the top, and I'm only getting rid of one of those signs with my negative du. So instead, we're going to have to do something else. Okay, so this one is not as easy. We're going to have to rewrite it first. Right, so if you, I don't know if you remember this. I mean, you should. It's just something you learned in Calc 2 when you were seeing how to do integrals of powers of sine and cosine. The idea is you can write sine cubed as sine times sine squared. Right, so I'm just writing it like this. Sine squared is the same as 1 minus cosine squared by the Pythagorean identity. Okay, so here we get integral of sine times 1 minus sine squared, everything over cosine. So if we split this, we get the integral of sine x over cosine x, which comes out with a simple u substitution, u equals cosine. Now we can worry about this other part. No, wait, this is not going to work either. Yeah, so how come there should be a way to do it because I'm asking you to do it. I'm just not sure what is that way.